Hi, everyone. Welcome to another Ansys Virtual Academy. My name is Pedro Chu. I'm the simulation practice lead here at KETIV. And today we'll be talking about, doing an intro to composite analysis using Ansys Mechanical. So just an agenda for today. We'll talk a little bit about composites, where it's being used, applications. We'll give just a very basic concepts on composite analysis. We'll see how the implementation is in the Ansys Mechanical. We'll do a very simple demo. And then after that, we come back for Q&A. So just a little bit about me. As I said, I'm the simulation practice lead here at KETIV. I joined KETIV recently, maybe 3 months ago, but I've been doing a finite element analysis simulation for over 30 years. I have worked in the aerospace, automotive, nuclear, heavy machinery, consulting. I think I have been everywhere, literally. They asked me to put some fun facts about me. I'm not sure if this is any fun or not, but I was born in Taiwan, and that's why probably you can put I grew up in Brazil. And then maybe that's why you see the name Spanish or Portuguese name in front of a Chinese last name. And I have lived in 4 different countries. So Taiwan, Brazil. I lived in Canada, where I worked at Atomic Energy of Canada and John Deere, and then finally the US. I think when we talk about composites, a lot of people associate composites with aerospace applications, and which is fair, because I think that industry is the industry that pushed adoption of high-tech materials into their components. But the composites has been around with the human species for a long time. So I think the first documented the use of composites came from the Mesopotamians about 3,400 years before Christ, BC, and where they would glue wood strips at different angles to create plywood, right? We also know that the Egyptians, they use a straw to reinforce the mud bricks. So these are all early uses of composites for strengthening material, to give it a different characteristics or properties for whatever use that they had. But today, composites is everywhere. We have composites being used in sport equipment, consumer products. The laptop that I'm using in front of me here has a lot of composites in it. Okay. Swimming pools, healthcare, prosthetics, crowns for your teeth, ceramics, medical equipment, transportation. So as I said, the aerospace industry pushed the envelope in terms of adoption of composites. So for example, the 787, I remember the goal was to have the full plane in composites, or at least a lot of main components all done in composites, and there was that really pushed the envelope in terms of not only manufacturing, but in terms of analysis, in terms of analytical methods to be used, so to properly account and calculate all the characteristics of components that you are designing. Okay, and one extreme use of composites, composite, being pushing boundaries for the use of composites is that Ansys was involved lately was in the 2017 America's Cup. The America's Cup is one of the most prestigious yacht competition in the world, where countries go and compete against each other. And when it comes to sports, competitive sports, there is no such thing as we'll compete just for the pleasure of competing. No, you are there to win. Okay, you want to win. And so the New Zealand team, they used Ansys to calculate, to optimize the sail. So the sail, as you can see, is probably one of the most important parts of the yacht, because you're capturing the wind and transforming that wind in a speed for the yacht. Okay, so you want this sail to have certain characteristics so that you can optimize the speed of your yacht. So you want to make it the strongest, the lightest, or basically you want to make it the most efficient sail that you can. So what was done in this project is that there were several geometric variations, several laminate compositions, stacking sequences, stacking orientation that were analyzed, and there was done a CFD analysis where you could capture the pressure loading coming from the wind, and then you apply the pressure, and then you calculate the optimize the strength of the sail so that you can have a certain type of a deformation and within allowable stresses, so that you can optimize, again, transferring the wind, the force or pressure into velocity or speed of the yacht. Okay. So the team in New Zealand won that competition in 2017, and so that's just an example of technology being used to optimize and the performance of the product that you're working with. Okay. So let's just look at some of the basic concepts of composites. So basically, in composite, you have plies, which is a group of fibers that are glued together, and these will form a layer. And then you have the laminate, which is nothing more than a stack of plies. So in a composite material, what you have is that you're going to have a stack of plies, and each layer on the ply, they will be comprised of a certain material. So each ply could be a different material. Okay. The amount of material, the thickness of the ply has to be determined, because that's going to, obviously determine how stiff this layer is going to be. And you need to define the orientation of your ply. Okay, because typically these plies they will be orthotropic material, and so the stiffness in different directions are going to be different. So that's why the orientation of the ply becomes very important. So as you build the stack, you are going to say, the layer one is going to be what material, is going to be what thickness, and that you define the theta, which is going to be the orientation of your ply. So in a finite element analysis, what you do is that you just basically define a material, and then you define a 0-degree orientation for your material. And then based on this 0-degree orientation, each ply could have a different theta angle, and that angle is defining the orientation of your ply. So in Ansys, there are several types of ways you can define a layered composite. You can use just the regular shell element, okay, so which is a planar element, and then for each element, then you define your layer number 1 on the bottom, all the way to the layer number n at the top. Okay, so this is just the regular shell element formulation that you have, but to assemble the stiffness of the shell element, you define the stiffness for each layer, and then Ansys will automatically compute the stiffness for your shell element. We also have a solid shell. So the solid shell, the formulation is basically the same, the formulation of a shell element, where the translational degrees of freedom would be, you know, the translational degrees of freedom, but the rotational degrees of freedom would be a combination of the relative translational displacements on the nodes on different faces. Okay, and for if you have a thick laminate, probably you want to use a layered solid. Okay, so these will be using the formulation of a solid element. Okay, and then again in the solid element you define the layer, the stacking sequence of the layers. Okay. So in a composite analysis, what you need would be the orthotropic material properties. So each direction would have a different properties. So you need to define that. You need to define the ply thickness, the orientation, the stacking sequence, and if you want to calculate a damage or failure criteria, you need to define what are the orthotropic strengths, the ultimate strengths, and which failure theory you want to use to calculate the failure indices. Okay, so here are the composite failure criteria available in Ansys. So we have the maximum strain, so where you basically divide in each direction the calculated strain by the allowable strain. Okay, and this will give you the failure criteria, for each material, for each layer. Similarly, you have the failure criteria we're using maximum stress. Concept is basically the same as well, but instead of a strain, you are using stresses in each direction. Then you have a more comprehensive failure criteria at SAIVU, which is probably one of the most widely used failure criteria for composites. Okay, so here you can combine the normal stresses with the shear stresses as well. And then you have the physical criteria, so like Hashin, that you separate the failure criteria for fiber and for the matrix, and for tension and compression. And same thing for the puck. Okay, so also you have the failure criteria for fiber, for matrix, and then the treatment for tension and compression would be different. Okay, so once you define the composites material in Ansys, you can use it just like any other regular element in Ansys. You can incorporate, you can bring it, you can combine it with the loadings from CFD, and it just becomes a regular finite element analysis. You can do a static analysis, linear, nonlinear, buckling, frequency domain, transient, and linear dynamics, in the explicit dynamics as well, if you want to do explicit analysis. And the failure criteria that I showed in previous slides were the first apply failure, but you can go beyond that. You can do delamination analysis, okay, and you can do a composite cure analysis as well, where the thermal effects it starts coming into play, and you want to calculate a residual deformation due to the curing process. So if you want to do a delamination, now this becomes a nonlinear analysis. Okay, and if you are using cohesive zone modeling, for example, you could, Ansys would define cohesive elements there, where the stiffness of that element becomes a function of the relative displacement between them. So as the laminar starts to opening, okay, you can define a force deflection curve where if the deflection is within a certain range, okay, no damage is inflicted to the material, and when you unload it, it is still linear and comes back to its original position. But once you go beyond a certain relative displacement, then you start incorporating damage starts coming into the model, okay? And then as you separate the lamina more, then you reach a point where damage equals 1, and then the material has failed there. Okay, so that'll be if you want to use what's called a CZM. You also may want to do the VCCT, which is an energy-based technique. So basically, you calculate the energy release rate, the necessary to separate or to cause a failure, and Ansys will just go and start splitting the mesh for you, and and then the crack can start propagating. Okay, so we are not going to talk about these today. That might be a subject for future AVAs. Okay. Today we are just going to talk about show a very simple composite model, and how we can define this as simple composite in Ansys Mechanical. So what I'm going to show in the demo is just a simple plate. I'm going to define 5 layers, and then the layer orientation will be 0, 45, 90, minus 45, and 0 degrees. The thickness for each ply is going to be 0.04 inches. I'm going to fully constrain at one end, and then just apply a 1,000-pound, pull or tension on the other side. Okay. So to do that in Ansys Mechanical, the first thing you need to do is that you need to insert a layered section. Okay. Once you define a layered section, you need to specify what is the geometry that is this layered section applies to. You need to define a coordinate system. So basically, you need to tell Ansys what is the 0 degree orientation for your ply. And one way to do that is through a coordinate system. So what you can do is you can define a local coordinate system in Ansys. And what Ansys will do is we'll take the x-axis of this local coordinate system, project it to the element, and that becomes a 0 degree orientation for your composite. Okay, and then you need to define layers. So to define the layers, you just select the worksheet option. Okay, and then when you define the worksheet sheet option, then you just define each layer, what is going to be the thickness, the material, and the orientation. Okay. So here is what I was talking about, the local coordinate system. So it will project the x-axis of this local coordinate system onto your element. Okay, that is going to be element by element, and that projection becomes a 0 degree orientation for your ply. And then when you specify the worksheet, okay, option, then this form comes up. You will insert your layers, select the material, define the thickness, and define the angle. Okay. So let me jump into my demonstration. So the plate defined, okay? And if I look at my material, I don't have my material here. So let me just go to my workbench. Let me go to engineering data, okay? And Ansys has some, predefined composite material. So what I can do is I'll just go to my composite material, and let me just select my this epoxy carbon 230 pre-preg, okay? So I have added the material here. I will update, and then actually here, if I okay, so if I want to define my damage, right? I can just click in here and drag it to my my material, and then you can see here here all the material properties for this epoxy carbon, right? So you have the Young's modulus, shear modulus, Poisson ratio, the ultimate, the stress limits, and so forth. And I just added the damage, and by default the damage is maximum strain, so I could change that to maximum stress, for example, right? And I can do maximum stress. Okay. And then I can just go and update my project so that these workbench then will just map all those properties to Ansys Mechanical. And now you can see my pre-preg is here, right, with all the material properties, right? And then I go back to my geometry, and I can just right mouse click, and I can insert layered section. But before I select the layered section, I said that I need to define a local coordinate system so that I can orient my plies. So I go to my coordinate system. I'll go insert a coordinate system. Let's just rename it. Call it the CS11. Okay, and in this case, a geometry, I can just say I want this to be, this will be the location of my coordinate system, and just let's leave it parallel to the global coordinate system. Okay, but this x-axis could be in any orientation, and just keep in mind then that it will take the x-axis, project it to the element, and that becomes a 0-degree orientation for my material. Okay, so coming back here, let me go and add a layered section. So geometry, let's select this surface. Okay, and for my coordinate system, I'm going to select the CS11 that I just created. And for layers, then I go and I specify worksheet. Okay, and then here it says layer 1 is going to be the bottom layer. Okay, and then here that's how you build your stacking sequence. So I'm going to add a layer to, and it doesn't really matter if it's above or below, because I'm just adding them here. So I have added my 5 layers in there, and then for all my layers, I'm going to select my pre-preg. This is the material for each layer. Okay, and then here is where I'll define my thickness: 0.04, 0.04, 0.04. Okay, and the orientation, I said I was going to go 0, 45, 90, minus 45. And here is my my laminate. So I have my laminate in here. From the bottom with the layer 1 to the top layer 5. Okay, and well, I ended up defining the opposite. I said I want to go 0, 45, 90, minus 45, but you know, that's okay. That's you know, so here you define the stacking sequence and then the orientation of the stacking sequence. Okay, so that is my my composites. You know, the mesh is here. I'm not going to change the mesh. Just accept say that this is a good mesh, and then I'm ready to come in here and then insert a fixed support, and I'm going to select this edge here, okay, and I'm going to define force. Okay, I'm going to define force in here, and let's define the components. I want them in the x direction minus 1000. Okay, so I have defined my loads, and then I can go and then request, you know, let's say total deformation. I can request maximum principal stresses, and in here I see the damage, and then you know, mechanical supports. You know, these failure criteria. The failure criteria that you don't see in here does not necessarily mean it's not supported by Ansys. You will have to just write a APDL to extract those to request those output. So that's just fiber tensile failure criteria. Okay, so I'm just ready to solve my model here. Okay, and I can look at you know, deformation, right? I can look at the maximum principal stresses, and and look at the, you know, when you look at the maximum principal stresses, you can specify which layer you want as well. So if I want layer 1, for example, right? Evaluate. So these would be you know, now my maximum principal stress at the layer 1, and then you can specify whatever layer you want here. And for the failure criteria, same thing here. So this is giving me the maximum failure criteria for all the layers. But if I want, I can specify which layer I want to look at the failure index, right? And so you can see that, you know, for here, this element here, it's at point, basically 0.1 is my failure criteria, failure index. Okay, so it's something, it's really simple to define these in Ansys. You have an option to define or request the failure criteria for each layer, or you can just do an envelope if you just, you know, do a 0 there. Okay, and then so this will be the envelope for all the layers in there. If you want to see, for example, for SIVU failure index, for example, then what you need to do is you need to define here a command, okay? And then you have to be familiar with the APDL commands to request that SIVU failure criteria. And so what you need to do is, let's say, you know, you set which load case you want to look at the results. You can define which layer you want, you know, the failure index to be plotted. So let's just specify F failure criteria maximum, so it's going to be the maximum across all the layers. Okay. Then I want to plot it in here for me. Okay. I want to set what view I want to look at the plot. So I know that my plate was in the XZ plane, so I want to go 0, 1, 0, so I can go have a top view of my plate. Okay, and then PL solve is the command to plot the element solution. So I want the fail, right? And the key for the Tsaivu is a TW SI. Okay. So what I need to do is I need to go back. I need to solve these again. And once I solve it, you can see that it puts this post output in here. And then now it's put all the Tsaivu failure criteria for me in this window here. Okay. So similar, if you want some other failure criteria, then you just go to your APDL and you maybe change the the Tsaivu to something else. Okay. Or you want to you can just look at some of the predefined or what the mechanical supports today in terms of failure in this index. Okay. So very simple. As I said, you just define a layered section in Ansys. Okay, you define your worksheet where you have every layer. You define the material, the thickness, orientation. Okay, then you set up your analysis just like any other analysis that you want to do. In this case, it was just a static. Linear static analysis, but you could have any type of analysis that you want. Layer the element. Composite is just like any other element in Ansys. You define lowest boundary conditions, and if you are interested in failure indices, then that is a post-processing steps that you need to do in Ansys. You just request the post-processing, and then you can just look at the results across all layers, or you can look at the results at each individual layer. Okay, so that's what I wanted to show. Coming back to the presentation here. As I said, this is just a very simple example that I showed you. A lot of times your geometry is not as simple or as straightforward as the one that I showed you. In a situation like that, you might want to explore using Ansys Composite Prep Post, ACP, so that allows you to do draping, apply drop off, and a lot more things that you can do. And automatically ACP will define all the apply orientation for you in Ansys. And then from ACP, you bring the resulting composite to Ansys Mechanical, and then you do the analysis in Mechanical. And then once you have the results, then you can go back to ACP, and then Tsaivu, Hashin, all the other failure criteria that I showed you in Ansys Mechanical. You need to define APDL. All those post-processing are available in ACP. So ACP is a lot more powerful than Ansys Mechanical for composites. Okay. And yeah, so I encourage you to look into ACP. Going to look into thermal and the electrical multi-physics simulation and then we are going to look at modeling, do a Joule heating using Ansys Mechanical. If you have any questions, comments, or you need to contact me, here is my contact information. My email is probably the best way to reach me. If you need any help from KETIV, okay, you can always send an email to support@ketiv.com, or you can call us directly. And if you need help, with your project, KETIV also has a consulting team here that is, ready and available to help you with any project and any needs that you have. Okay. So that's all I had. Not sure if we have any questions in the.
Great job, Pedro. Thank you so much for joining us and leading the session. It looks like we have one question. It says, how does Ansys combine the individual layers in a layered section? Does it create a new combined orthotropic material using rules of mixtures, etc.? Does it use the layer info in tandem during run?
It will just basically, add the stiffness that you have in each layer, okay, and add them up together, and just it will come up with the element the stiffness matrix basically. So it will calculate internally the composite. You have the A, B, and D matrices, which would be the stiffness in the bending, shear, and then and then use all those terms to assemble the element stiffness matrix. So basically, the information that you use for each layer will calculate the stiffness for each layer, and Ansys will combine the stiffness for every layer to give you just a simple element stiffness matrix.
Okay, awesome. I don't see any other questions in the chat, and our friends on YouTube don't seem to have any questions either. So thank you so much for coming on and teaching us something new today.
Thank you for organizing this, and thank you all for attending, and really looking forward to next month's AVA. I hope you guys can join.